Visual Inertial Odometry using focal plane binary features. We will be going over the background, problem statement, critical design, results, and conclusion and next steps. This is the background of our FPSP VIO work. Conventional camera technology usually captures an image, does feature extraction, feature matching, and pose optimization and matching on some external processor. FPSPs are state-of-the-art where we alleviate some of the processing, such as feature extraction on the vision chip itself. Here are some more benefits. FPSPs and their potential with VIO and VIO systems. You can see here that conventional camera technology suffers from motion blur. FPSPs here below actually can track very robustly. They use single instruction multiple data hardware on the FPSP, which not only alleviates computing power, but also provides higher frame rate processing and low latency, ideal for robust tracking. This was a prior work known as BIT-VIO, where here are some contributions. It was able to track at 300 FPS, outperform state-of-the-art monocular SLAM. You can see here there was a robust feature matching scheme using bitwise rotations using the FPSP, and it was able to deal with 4 to 5 hostile motions. But is there more complex state estimation on the FPSP? And so this is the problem statement of our work. We build off of BIT-VIO, presenting a 60OF VIO algorithm known as BIT-VIO. The contributions are listed where we fuse it with a 400 Hz IMU with vision at 300 FPS. We have new uncertainty propagation from 2D to 3D reprojection on the pose, and we do extensive evaluation. This is where our BIT-VIO algorithm can track a 60OF pose at 300 FPS, and you can see fusing it with an IMU, visual inertial pose estimation is done at high frame rates using the FPSP. You can see here that the roll, pitch, and yaw of our VIO, visual inertial FPSP state estimation algorithm, can track very fastly and robustly. This is the advantage of using FPSP for high frame rates. We will now be going over the critical design or algorithm of our work. To the left, we have an iterated extended Kalman filter, and to the right, we have a vision algorithm, which is the BIT-VIO algorithm. You can see here in red, at the top right, the SCAM5 FPSP does the corner and edge feature computations and processing entirely on its vision chip. And so this is the novelty of our work. You can see here that to the left, we show a trajectory which shows how IMU alone drifts here in green. Our BIT-VIO algorithm alleviates this drift, providing a trajectory closer to ground truth in red. IMU alone state estimation is not enough, it's not accurate enough, and so that's why we fuse it with this new novel vision chip. You can see here the SCAM5 FPSP computes and does computation and processing of the corner and edge features entirely on itself. You can see here you have raw edge and corner images, and they are done on the SCAM5 FPSP, and they track very robustly. This is the novelty of FPSP SCAM5. Corner and edge features are computed on the FPSP and operates at 330 FPS. We use fast key point detection. It is challenging to track robustly on features because feature extraction suffers from noise and analog computation, and multiple features are extracted per visual corner. Since SCAM5 performs computations using an analog circuit, corners are not reliably extracted in every frame. To alleviate this, we use Riku Murai's bit feature descriptor, which uses those local edge information as well as the corner features. And in this sense, we have a descriptor which is space efficient and fast to compute, utilizing fully the advantages of the FPSP. Here we create 3 concentric rings, here in pink, blue, and in orange, and we account for rotation invariance on these said corners by doing bitwise rotations on these 3 rings independently. You can see here that we create a 7x7 patch and is used to sort of fit into a single 64-bit unsigned integer, and this allows the patch data to be converted into rings efficiently using bitwise manipulation only. Again, this descriptor is space efficient and fast to compute, utilizing fully the advantages of the FPSP for robust frame-to-frame tracking and map-to-frame tracking. This is the critical design of our work, where again on the left we have an iterated extended Kalman filter, and to the right we have BIT-VIO. You can see that the SCAM5 FPSP computes the corner and edge features, where we are alleviating processing and making use of the high frame rate for fast and robust feature tracking. This is basically the framework where our frames here are listed. We have the IMU, it could be a black box IMU, and you can see here we are fusing it, Vision IMU fusing it with a SCAM5 FPSP. Again, the conventional camera technology would basically have motion blur, but our SCAM5 FPSP can track very well. And so that is our contribution. Here are now some results and progress and some experiments to our work. You can see here that the problem of high frequency noise of BIT-VIO in complex fast motions, we can actually alleviate that. And here in blue, BIT-VIO, the prior work, has high frequency noise, but our BIT-VIO in green alleviates this. In case here you have when perhaps BIT-VIO is tracking very poorly and the calibration is poor, right? You can see here in blue there is high frequency noise of BIT-VIO, but in green our BIT-VIO algorithm uses the IMU to account for this. And this is a case where we have sharp turns and motions in this demo where we are still able to track very robustly. And see here in BIT-VIO, again, high frequency noise, but our BIT-VIO algorithm outperforms this. And so generally here are some absolute trajectory error statistics where we show that on the left, there is high frequency noise of BIT-VIO in blue, but green our BIT-VIO algorithm, because it has lower absolute trajectory error shown in the table on the right, it actually silences that high frequency noise and is closer to ground truth. You can see here when we do error mapping on the Z and X plane, you can see that BIT-VIO to the left has high frequency noise where there are red tail regions of high noise, but here to the right, our BIT-VIO algorithm tracks very close to ground truth and is closer to ground truth than BIT-VIO. You can see here when it's IMU alone, it will drift. And so in this case, that's why we do visual inertial fusion. And you can see here in blue, our BIT-VIO has lower RMSE error generally than BIT-VIO and IMU alone. And that is the conclusion of our work. We have presented the first ever 6DOF FPSP vision IMU state estimation algorithm. In future works, we hope to extend it using a tightly coupled approach.